Welcome to Unit 7 of this course. In this unit, we will be seeing what is called linear temporal logic. This is going to be a formalism for specifying properties. In the first module, we will give an introduction to linear temporal logic. Henceforth, we will call it LTL. So let me recall the big picture again. We are interested in verifying transition systems. More precisely, we are interested in checking properties on transition systems. And for checking properties, we were using expressions of this kind. In this week, we will be extending these expressions to this full-fledged logic called linear temporal logic. This is just a formalism, a way of specifying properties. So here is a more detailed picture. Usually we have a transition system and every state is labeled with the set of atomic propositions that are true on that state. We started with a finite set of atomic propositions P1, P2, whatever they are, and then we evaluated them on the states and we got this transition system along with atomic propositions evaluated. Suppose there is a property P. What is a property? A property is just a set of infinite words over the alphabet, the power set of AP. A property is going to be words of the form, say, set of P1, set containing P1, P2, set containing P1, P2, and so on. So a property is a set of infinite words over the alphabet given by the power set of P1, P2. So every letter in that word will be a set of atomic propositions. Suppose somehow you have specified the property. When do we say that the transition system satisfies the property? If the traces of this transition system are contained in P, then we say that the transition system satisfies the property P. We have seen this multiple times, but it's good to keep recalling this again and again because this is the key concept in this course and everything else is built around this concept. Now, for specifying properties, we have seen multiple formalisms. We could either specify using this GF, XGF, etc. We also saw a way of specifying safety properties using finite automata. In the last two modules, we have been seeing omega regular expressions for specifying properties. The most convenient and common formalism used for specifying properties is an extension of this kind of expressions GF, X, GF, etc. and that is called linear temporal logic. Finite automata and omega regular expressions are useful in a theoretical sense, but for using model checking tools, it's important to understand linear temporal logic. As long as you understand linear temporal logic and you know how to model systems, you can use model checking tools. Let's now see what LTL is step by step. Expressions in LTL will be called formulas. Let us now see how to build LTL formulas. Take a look at this execution. The trace of this execution is going to be an infinite word consisting of sets of atomic propositions. What I will do now is to build the syntax of LTL in the sense, how do we form formulas in LTL and when do executions or when do traces satisfy them? Okay. Firstly, true. The word true is going to be an LTL formula. Take it for granted. Now, what is the role of true? every execution satisfies true. In other words, every infinite word over the power set of atomic propositions satisfies true. Every atomic proposition is also an LTL formula. In the sense here, P1 would be an LTL formula, P2 would be an LTL formula. When does a word satisfy P1? You look at the first letter in that word, and if that first letter contains P1, then this entire word is said to satisfy P1. Similarly, this word satisfies P2 because P2 is also there in the first letter. Just assume now that true, P1 and P2 are LTL formulas. So far it is not interesting. Let us build more complicated LTL formulas which would give us means to express more interesting properties. Suppose phi1 and phi2 are LTL formulas. For example, P1 and P2 were LTL formulas. Then this symbol stands for AND. So this reads as phi1 and phi2. Here P1 and P2. P1 was an LTL formula, P2 was an LTL formula. So P1 and P2 would be an LTL formula. In particular, this formula is true on this word because both P1 and P2 are true in the first letter. Suppose we had an atomic proposition P3, then you could have said that P3 and P1 and P2 would be an LTL formula because P3 is an LTL formula. Now P1 and P2 is an LTL formula. So you can build P3 and P1 and P2 using this rule. This says that if phi1 was an LTL formula, you can add this notation in front of phi1 to form yet another LTL formula, and this notation stands for NOT. Okay, if phi1 is an LTL formula, then you can add a NOT to say that NOT of phi1 is also an LTL formula. Look at this word P2, P1, P2, P2, P2. Look at the first letter. It does not contain P1. So this word is said to satisfy NOT of P1. However, this word does not satisfy NOT of P1 because P1 is indeed there. Okay. For now, you just need to know that if phi1 is an LTL formula, then NOT of phi1 is also an LTL formula. This is a way of building formulas. You started with true, then you started with Pi, which means P1 and P2 here. So each P1 and P2 are LTL formulas. Given these, you can form ANDs and NOTs. For instance, P1 and NOT of P2 would be an LTL formula. P3 and NOT of P1 and NOT of P2, this would be another LTL formula, and so on. Now comes the first interesting rule, which says that if phi is an LTL formula, then X phi would be an LTL formula. See, so far when we were looking at true Pi, phi1 and phi2 and not phi1, we were just looking at the first letter in the word. We were not caring about the rest of the word at all. We said that something satisfies these formulas just by looking at the first letter. Now comes the first operator which looks at the rest of the world. In particular, x5 is true if the next letter contains or rather satisfies 5. For example, here xp1 is true on this word because the next you leave the first one. Normally in CS we count from 0, right? So this is position 0 and this is position 1. So x of p1 is true if this position, where this is position number 1, contains p1. Okay, here x of p1 and p2 is true. For example, if I had added x of p1 and p2, that would be true on this word. Similarly, x of p1 is true here because p1 is present here. However, in this word, x of p2 is not true because p2 is not true here. On the other hand, x of not p2 would be true because not p2 is true in this position. So x of not p2 would be true. See, this is what is written here. Since p1 is true and not p2 is true, you can even say that x of p1 and not of p2. Okay, we will see more examples and hopefully this will become clear. But for now, you need to know that these are the rules for building LTL formulas. Given these rules, you can even say not of x of p1, not of x of p1 and p2, and not of x of p2, for instance, because you can keep using x's multiple times. So since x5 is again an LTL formula, you can say x of 5. For instance, here x of p2 is true because you go next once and next one more time, p2 is true. Similarly, x of p2 is true. X of not p1 is also true because p1 is not true here. This x is a way of jumping inside for certain number of steps. However, if you write 1x, it just jumps once. So there is no way in which we can go far in this word. You can go as far as there are as many x's. The last operator that we are going to look at addresses this going farther in this word issue, and this operator is called until. Phi1 until phi2. This says that in a word, so phi1 and phi2 are LTL formulas. So here is an example where we are looking at p1 until p2. This says that you go to the first point where p2 is true. Till that point, p1 is true. Moreover, it just doesn't say this, it in fact asks that p2 should definitely be true sometime in this word. So p1 and p1 until p2 means sometime along in this word p2 is true, and till then p1 is true. You don't need p1 to be true here in this place, but till that time p1 is true. Okay, another example maybe here p2 until p1 is true because p1 is true here, and till p1 becomes true, p2 is true. So x and u are called temporal operators. They are used, so temporal means related to time. So by time we do not mean precise time as in 3 units, 4 units and so on. This just says that along the word sometime p2 is true and till then p1 is true. This x allows to go one step ahead. So X and U are called temporal operators, and since we are working with words, it takes the name linear temporal logic. So this is the syntax, in the sense, using this grammar, you can form LTL formulas. For example, X of P1 until P2. In particular, here X of P1 until P2 is true because from the next step, in this step, is P1 until P2 true? Yes, because P1, P1 and P2. So you can even ask for X of P1 until X of P2. Things like this. You can keep nesting X's and U's and nots and ands using this grammar. Okay? Let's see some more examples. So this says not of P1 until P2. It is in fact true because look at where P2 is true. P2 is true here, but till then P1 is not fully true. P1 is true here, P1 is true here, but here P1 is not true. So P1 until P2 is not true here. In particular, this execution satisfies not of P1 until P2. This formula says that P1 until P2 and XP3. Let's first look at this formula. P2 until XP3. Here P2 is true and XP3 is also true. This is the point where P2 and XP3 is true. Until that point, P1 is true. This says that P1 is true until this formula holds. P1, 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 and at this point, P2 and XP3 is true. What about this? This says that X of not P1 until P2. Let's see, from this step, not P1 until P2 should be true. Look at this. From here, look at the point where P2 becomes true. Here is the point where P2 becomes true. And till that time, P1 is not true. So, this word satisfies X of not of P1 until P2. Let's now use the expression true. This says that true until P1. This means that some point of time P1 is true, and until that point you don't care what to be true. In this sense, this says that since true is satisfied at every position, the formula true until P1 just says that at some point P1 is true. Okay? If it had been P2 until P1, then it's not satisfied here because P2 is not true here. However, when I say true, it means there is no constraint till P1 is true. That's why we said that true is satisfied by every word. We will see a formal definition of these things in the next module. However, it is important to get the intuitive idea clear. True until P1 just means there is no constraint. However, at some point P1 should become true. Let us look at the next example. Listen carefully here. This says that true until not P1, and the whole thing is negative. Firstly, what is true until P1? True until P1 means sometime in the word P1 should be true. So when we say true until not P1, it means that sometime in the word P1 is not true. So for instance, here true until not P1 is also true because sometime in the word P1 goes off. When we say not of this, it means I will not be able to find a position where P1 is not true. In other words, I will not be able to find a position where not P1 is true. That means everywhere P1 is true. Let me repeat. True until not P1 says that P1 is false sometime in the word. When you say not of true until not P1, it says that it is not the case that P1 is false sometime in the word, which means P1 is always true in the word. Okay? These two might look similar. Indeed so, because this is just f of P1. So f of P1 can be written as true until P1. Remember, f of P1 said that some point of time P1 is true. Now what about this? This is just g of P1. So g of P1 can be written using operators given in this grammar. G of P1 is just not of true until not P1. It is not the case that P1 becomes false at some point in the word. Please try to understand the meaning of FP1, GP1 in terms of the until. As long as you realize that F and G can be written using until, that's good enough. But it's also important to know that F of P1 stands for some point P1 is true and G of P1 stands for everywhere P1 is true. So this is easy. And we will be using this F and G henceforth. So here are the derived operators. Here we had and not. How can we write or? When I want to say phi1 or phi2, it means that one of them is true, which means it is not the case that both phi1 and phi2 are false. That means it is not the case that not of phi1 and not of phi2 is true. Okay, so or can be written using just and not. What about implies? Implies says that if phi1 is true, then phi2 should be true. Note the if here. If phi1 is true, then phi2 is true. In particular, if phi1 is not true at all, then this implication holds. This is written by not of phi1. However, if not of phi1 is false, in other words, if phi1 is indeed true, then phi2 should be true. So this is taken care by this operator, not phi1 or phi2. Either phi1 is false, in which case this will be true, or if this is false, that means phi1 is true, then phi2 will become true. F and G were what we saw before. F of phi is just true until phi. Now G of phi is just not of true until not phi, which means not of f of not phi. It is not the case that I can reach not phi at some time, which means always phi is true. We can form more operators out of this simple grammar. However, let me list down two important things which keep recurring again. The operator GF phi. We have seen this before. GF phi says that everywhere f phi is true. From any point in the word, I will be able to reach a point where phi is true. This means that phi is true infinitely often. Now, what about fg phi? This says that at some point of time, g phi is true, which means there is some point from where phi is always true. See, G phi means always phi, right? And F means that from some point phi is always true. These two are important expressions that you could try to remember or understand. Many properties can be written using GF and FG. Let's see some more examples. Now, on a proper transition system, remember the mutual exclusion protocol using the semaphore Y. Let's define the following atomic propositions. Instead of P1, P2, we are writing crit1 to denote the fact that process 1 is in its critical location. Crit2 means process 2 is in its critical location. Wait 1 means process 1 is in its wait location. And wait 2 means that process 2 is in its wait location. This is the new SMV syntax. So I'm just marking them using these atomic propositions. Let's write some properties. Safety property. Both processes cannot be in critical section simultaneously. This means that always either not of crit 1 is true or not of crit 2 is true. Okay? You can write it in another way. It's not the case that f of crit 1 and crit 2, this is an equivalent formula. G of not crit 1 or not crit 2. Always in the execution, either process 1 is not in its critical location or process 2 is not in its critical location. What about liveness? Each process visits critical section infinitely often. This is fairly straightforward. Once you know that GF stands for infinitely often, so GF crit 1 and GF crit 2. Crit 1 is true infinitely often and crit 2 is true infinitely often. So this is a summary of LTL. Every LTL formula is formed using this grammar. A grammar is just a set of rules to build formulas. We have seen examples. Please go through them again and again and again. F is derived using until and true by saying f of phi is true until phi. G is just not the case that f of not phi. Okay. Over time, these formulas will become clearer and you can specify properties that you encounter using these expressions.